video covers section 10.7 probabilities, which is the last section of chapter 10. The section will be in your take-home exam, so please make sure you take notes and you work all the problems out. So we started the class by Miguel writing down the definitions, so thank you for that, Miguel. We already have them here, so I'm just going to read them out loud. If you need to pause the video, feel free to do so. The empirical probability applies to situations in which we observe how frequently an event occurs. And so right here, the way we're going to calculate it is by dividing the total number of events or occurrences, and that will be divided by the observed number of events that certain thing occurs. Now, probabilities, they go from 0 to 1, with 1 being 100%. Okay? So that is when you are 100% certain that that is, I don't know, like for example, his name is Ezekiel. I'm 100% sure that his name is Ezekiel. So the probability that his name is Ezekiel is 1. All right, now 50-50 chance, of course, that is half. But if we talk about a percentage, that will be 50%. But in probability, we use decimals a little more, especially for empirical probability. So we will say something like 0.5. There's a 0.5 chance. I know you guys have heard on the news, sometimes people will say like, there is a 20% chance of rain, or 30. So that would be like, there is a 2-point chance of rain, a 0.3 chance of rain. And yeah, that falls into maybe unlikely, but to me, if I'm in El Paso and there's a 30% chance, to me that's like a pretty significant probability. So let's move on and see how we're going to solve this problem out. So right here, this is the info. It is true, and it does apply to breast cancer and a mammogram. Now, do you guys know what that is?
It's a screening that they do to check for breast cancer.
Yes, it's a screening that they do to check for breast cancer. Now, could any women get a mammogram? No. You have to be of a certain age. What age? I think it's 40, over 40, maybe 45. And so when you girls are of that age, you need to be very self-conscious about doing those exams, okay? Especially if there is a family history of breast cancer. Especially if this comes from your mother's side. I didn't know that. But like to have an aunt who had breast cancer on your dad's side and your mom's side is kind of different, okay? So be conscious of that. What will happen if you get a mammogram and you're not 40 years old?
No.
Well, actually, it's a great point because a mammogram produces a lot of radiation. But if you have a mammogram and you're not, like I had one when I was probably like 30, they couldn't see anything because my breast tissue was not dense enough for them to see it. And I did get one because my aunt had breast cancer, but she is on my dad's side, so it was not like a huge deal. Okay? So.
Wait, so what if you're gonna get breast cancer when you're like young? How do you?
Oh, great question. So what they had to do with me, a sonogram, a breast sonogram. Oh, I'm sorry, breast ultrasound.
Yeah, they did one on me too.
Mm-hmm. Because of family history. So yes, if you have a family history, it's never too early to start checking. Yes. There's also a DNA test that you can have, like if your mom or your maternal grandma had it or something like that, there's a blood test that you can have. So moving on. So mammograms are very important because it's actually one of the leading causes of death amongst women. Now, maybe not between cancer, there's only one cancer that causes more death amongst women. What would that be?
Ovarian?
Cervix. Or the uterus cancer. Number 1, breast is number 2. So a person who studies statistics, for example, they could work at a hospital. I have a lot of friends who work at, what is this place called? Texas Tech, the University Medical Center. And so what they do is they analyze all the data from research that is going around, like the doctors are researching something, it could be other medicine, a test, something like that. And so they analyze that by using empirical probability, and then they're able to make suggestions or make determinations, okay? So yes, math is useful, even in medicine. So let's see. When women turn 40, oh, right, Crystal. Their gynecologists typically remind them that it is the time to undergo I can't say that word. Mammography?
Yeah, mammography.
Screening for breast cancer. Oh, interesting fact. Can guys have breast cancer?
Yes.
Yes, they can. At the VA, the Veterans Clinic where I go to, my doctor has two male patients with breast cancer. One is in his 20s, and one is in his 60s. I thought that was very interesting, because you don't have to be like really old to have it. So even you guys, you might want to do some. So, well, maybe not to that extent, but you could always do a self-exam. I'm sure if you Google it, you could find it.
Yeah.
Well, there's certain things that
Actually, one arm has to be lifted.
Yeah.
yes, you look for bugs.
Ms. Bevan, I volunteer at a clinic and they teach the woman how to.
So you know how.
Yeah.
So would you be okay? Not in class. Only with a group of girls to teach them. Maybe we could arrange for that, because that, and then they can pass some of the info to their sisters, moms, grandmas, everybody. Okay. So let's get back to the problem. The problem on our handout, which is not as big as the real problem. So their gynecologists tell them they need to check the breast. So if we look at that table, which was a screening between 100,000 U.S. women between the ages 40 and 50. So the total subjects who were screened were 100,000. And do we have a question here? No, right?
No.
The question's on the next slide. Oops. Okay, so we're going to use that. This will be our first question. We're going to use that table to find the probability that a woman aged 40 to 50 has breast cancer. So this is how we're going to do it. Probability of having breast cancer. Yes.
What's the difference between a positive mammogram and a negative?
So a positive mammogram, I'm assuming they detected something, some type of body. But after that, the next step to test it will be biopsy to see if it is benign or malignant, like it has cancer.
Because it says even if in a negative mammogram, it still has a section for breast.
Well, we're going to get into like what it means to, okay, so positive, negative, it just means that they found something, they didn't find anything.
But then it still says breast cancer. Yeah, it says breast cancer.
Well, that's because there's always a margin for error. Yeah, but we'll get into that. Yes. Let's just start with an easy question. So probability that a woman between that age will have breast cancer. So let's see. The total of patients, if you add this one plus this one, is 100,000, right? Yes? Okay. How many of those 100,000 had breast cancer? Don't worry. Wait a second. Let me read the question again. So the people who had breast cancer will be right here. Now, let me tell you what happened. 720 women that got a correct result, but 80 got a negative result when in fact they had cancer. That is a huge issue. Why do you guys think that could have happened?
Well, then they don't know that they need to go get treatment.
Well, maybe I will look for a second opinion, but what do you guys think could give you a negative result if you have breast cancer?
Plastic surgery.
Well, yes, maybe the breast implant got in between, or maybe the person density, very good. Maybe the person didn't know how to use a machine,
Yeah, that's what I was thinking.
or human error. That's a very nice way to say it. Another one is that maybe the cancer was too small to be detected, but it's still there. Okay, so let's add, what is 720 plus 80?
800.
800, okay. So out of 100,000 women, I'm sorry, 800 women, out of 100,000 women, 800 had breast cancer. So if we divide that, what do you get? 0.008?
Yeah.
Okay. Oh, well, yeah, right? We just move that 3 decimal points. I should know that. Okay, that's the probability there. Now, let's see. Among women without breast cancer. So now I'm cutting the table. This table that you see here is the same one on your first slide. But now we're just focusing on this part, the women without breast cancer. All right? So let's go back. Find the probability of a positive mammogram. But now we're not looking at the whole sample of 100,000 women. We're only looking at the sample of women without breast cancer. So how many women are there without breast cancer? So let's add these two quantities. That's 0. Yeah, any help?
90,000.
98 or 99?
No.
Okay. So 99,200. So those women have no breast cancer. So what is the probability that amongst those women, they have a positive result? So we're looking at positive results. So that will be 6,944 over 99,200. And then, can you guys please give me a decimal?
That would be 0.07.
0.07. So if you don't have breast cancer, is it likely that you can get a positive result? Not really, but you could still get a pretty good scare, right? I would.
That's pretty high, right? That's like 70%.
Yeah, I would
That's
completely freak out. So I would go and get a second opinion. That's what I would.
That's it.
Okay, so if you ever get that, nothing's lost. You always look for a second opinion.
Yeah.
All right, now among women with positive mammograms, find the probability of not having breast cancer. Now we're looking to look at, this is our sample space. All the women with positive mammograms. How many are those? So we need to add
5,664.
Thank you, Viviani.
I mean, 7,000.
7,664.
7,664. Very good. 7,664. And out of those, we want to find the probability out of that sample space that they had not having breast cancer. So how many did not have breast cancer? Okay, can you guys give me a decimal, please?
That's 0.90605. So that'd be 90%.
Okay, so let's look at false readings, the ones that were wrong. So here we have people who are testing positive but they don't have it. That's a pretty high number, isn't it?
No.
Well, the 720 do have it.
Okay, no, I'm sorry.
Wait, this has something in the.
People do not have it. So it's very likely that you don't have breast cancer and you could still test positive. Why is that? Besides the human error.
Because doesn't it like just test to see if there's something in?
They test for just a mass,
Yeah.
right? Mhm. What were you gonna
The cyst that we were.
Okay. There's a disease called hold on. Not that one. I got it. Fibrocystic tissue. And so, when you have that, it depends. Remember what we talked about periods, right? Up and down, right? What's the period? 28 days. So during those 28 days, not only your the lower part of your reproductive system goes through changes, also the upper part. Okay, and so your breast goes through changes as well. So at certain times of the month, they are more dense than others. So that could also be subject for error. Like they could misread and be like, okay, that's just a cyst. It's not really benign tumor or malignant. Now, if you look at the probability of people who do not have breast cancer and people who have no breast cancer and get a positive result, seems like we're saying the same thing. The sample space of 99,200 is talking about women without breast cancer. And the sample space that we're talking about here is women with a positive mammogram. So, let me see if I can explain this better. Right here, we're trying to find, out of all the people with positive mammograms, who got the incorrect result. People who did not have breast cancer. And part B, we were looking at between all the people without breast cancer, how many of them got a positive result? Let's do the other ones and then maybe they will make more sense to me. So let's see. Find the probability that a woman aged 40 to 50 has a positive mammogram. Now, let's look at the big table. This one from the beginning. And so what will be the sample space for that question, guys?
100,000.
All the women. And how many had a positive mammogram? We have it here, right?
Yeah.
Okay, can you guys give me 0.07? Oh, you're doing it in your head. Okay.
Well, it's 0.07664.
Yes.
So not a lot of people actually do this. Well, out of these 100,000 actually tested.
Well, 100,000 people is a substantial sample. For example, the guy who did the study on vaccines. Does anyone here is against vaccines? Sorry if I offend you, but I'm just gonna say this. That guy did not know what the heck he was talking about, and did his whole study based on 7 people who he didn't even follow for years. And so that vaccines cause autism is a complete lie. Okay? Just so you know. If you know someone who doesn't believe that, send them my way. I will convince them. There's a lot of evidence that I can talk about. So, now let's see, among women with breast cancer, find the probability. Well, Dima, going back to your question, I know it doesn't look like a big number, but if you change this to a percentage, what would it be?
7.48%.
Like let's say 7.7%. Now, if you just look at a group of 100 women, that means that 7 or 8 women will have it. So then it sounds like a lot, right?
But it's not as bad.
As others, no. That's cervix cancer. That is way higher.
So it's kind of like really rare.
No. This is not a rare cancer.
No, I mean like breast cancer. Is it like rare?
No.
You just said
That's what you're saying. No, breast cancer is not rare.
it's suicide of 100,000 people.
Do you guys? Okay, let me teach you guys something, guys. What's the leading cause of death in men? Cancer. Cancer what?
Testicular.
Testosterone.
Testicular.
Before testicular, prostate. Prostate. Okay, now among women with breast cancer, find the probability of a positive mammogram. Now, let's only look at the women with breast cancer. So, not that one, the other side. Oops, did I go the other way? What do you say, Sean? 800? Thank you. So, out of 800, how many of them had a positive result?
720.
720. And as a decimal, that will be
0.9.
0.9. So if you have breast cancer and you go to get a test, to get checked, there's a high probability that you're going to get a positive result because you have breast cancer, right? So there's still a little margin of error that you could get a negative result. What do you guys think the probability will be? 0.1, yeah. That a person with breast cancer could go and have a negative result. And you know that one thing, guys? This type of errors also occur with pregnancy tests. I don't mean to scare you, but it's the truth. All right, next. Among women with positive mammograms, find the probability of having breast cancer. So now, can you guys tell me how many women got positive mammograms? I think we had that up here. This one, 7,000?
Yeah.
7,664. How many of them
720.
actually had cancer? 720. And then I'm going to need a decimal from you guys.
Oh, 0.093946. 3946.
Okay,
Wait, what happened to
0.093946. Okay, so that is empirical probability where you look at some data and you analyze it and you make conclusions, assumptions, and all of this. Now, the next probability is theoretical, and thank you, Miguel, for writing the definition for us. So, an experiment, okay, first of all, theoretical probability will be based on experiments. So let's first define what is an experiment. So it is any occurrence for which the outcome is certain. The sample space will be the set of all possible outcomes of an experiment. And we're going to use S for sample space. Now, we're going to use the same idea or principle that we were using with theoretical probability, meaning that we're going to divide the number of outcomes by the total number of outcomes in the sample space. All right? Yes.
Can you go back up?
So a very common example here about theoretical probability is when you toss a coin. And so it is very common because there are only two outcomes, right? So the sample space is right here. We have it denoted as a set. That's why we have the curly brackets. And so if I ask you a question, what is the probability that you will get heads if you toss a coin? 50-50. Let's try it as a fraction and then we'll go to the fifth. It is 50% or 0.5, very good. And if we use this one, it will be, what is the total number of outcomes?
1 and 2.
Yeah, one.
But if we consider both, 1 plus 1?
2.
2. And how many ways can you get heads?
1.
1.
Yeah.
So 1/2, 50%, 0.5, they're all valid answers. Yes. This one is also about theoretical probability, and it is when you roll a die, and that is singular for dice.
Oh,
Yes.
I thought it was backwards.
I could be wrong.
No, you're right.
Am I
One
right?
is a dice.
Okay.
No.
2 is
One
dice.
and you roll 2 dice.
No, I'm pretty sure.
Okay, now I'm confused.
Dice is
Multiple weight.
Well, let's look at the question.
Typo.
Right here it says a die is rolled. So to me that's just 1.
You're correct.
roll 1 dice.
Yeah.
Yeah.
Okay? Okay. So what is the problem? How many faces does a cube have? 6. So that means you have 6 probabilities, right? 6 possibilities. What is the probability of getting a number that is less than 5?
4.
So how many numbers are less than 5? 1, 2, 3, and 4. So 4, and then you guys, we could say divide by 2, so that would be 2/3. Can you guys give me a decimal?
0.66 repeating. Or 67.
Okay.
No, it's already 6. No, 7. Right, 7. 7.
Okay. Now let's look at this other one here. 2 ordinary 6-sided dice. Oh, so that's plural. They are rolled, and yeah, sure. Who's here? Okay. So 2 ordinary 6-sided dice are rolled. What is the probability of getting a sum of 8? And so I have that one right here marked for you. Well, actually, it was from Brooke. And if you consider the first die rolls a 6, and then the second die rolls a 2, they will add up to 8, right? Also, if the first die rolls a 5, and the other one a 3, or a 4 and a 4, 3, 5, 2, 6. So how many possibilities? What is the total of combinations that we can have rolling two dice? So in this case, the order does matter because we are differentiating between the first and the second die. So if you count them all, how many combinations are there? 36. So out of 36, and how many of those can you get a sum of 8? 5. Very nice. Can you guys give me a decimal for that one?
That would be 0.138889.
Okay. That will be it. Now, can you guys answer the next one? You could use the same image. The checkpoint 3. you want to get a sum of 5. The sample space is still the same, so it's 6. So at 5, we could have here
1, 4,
1. Like,
Yeah, it's still 21.
so the problem, and I should probably, I'm being a little lazy. I should be writing this. The probability of getting a sum of 5. And that will be how many possible? 1, 2, 3, 4? Out of the total outcomes?
36.
And that should reduce to 1 over 9, correct?
Yes.
Okay. And now for decimals, what are we writing?
0.1 would be.
All right. Very good. Let's go to the next slide. Ooh. Hard. Okay. So computing theoretical probability without listing an event in the sample space. So sometimes you're not going to be able to look at sample spaces. Like for example, for empirical, we must have tables, we must have data. For theoretical, you don't really have to list all the outcomes like they are listed here. Okay? As you do more problems about probability, you get more used to them. And so that becomes a little unnecessary. And let's just analyze this little picture here that I have for you. I don't like cards at all. I'm just being sarcastic.
Yes.
So, okay, how many suits do we have?
4.
4. And what do we call a suit? We call the heart, the diamond, the club, and the spade. I have a little hard time drawing that one.
It's pretty good.
Thank you. Thank you. And so, how many colors?
2.
2 colors. We only have red and black. And how many denominations? That means like numbers and 13. And we all know what they are, right? So we start with A, with the A's, and then 2, 3, all the way to 10. And then we have the jack, the queen, and the king. Am I missing one? No. And of course, for purposes of blackjack, the A could be a 1, or it could be
An 11.
Okay.
Are we going to do that?
Video. So let's answer the question for example 4. You are dealt 1 card from a standard 52 card deck. Find the probability of being dealt a heart. This is so easy. So we have 52, and we're trying to find the probability that you get only 1 card and you get a heart. How many hearts are there? 13. So that's the probability right there. Now, when you do your homework on my math lab, guys, make sure, yes, let's reduce it to 1/4. And make sure you read if they want the answer in fraction. If they say exact answer, it will be that.
Exact will be a fraction?
Yes. Like in a rational number.
If they don't specify exact.
You know what I will do? I will look at the example and see how they answer. All right, next one. So, who can read this for me, please? Thank you, Bastian. You're next. You're next. You're next. Don't worry. Oh, my coffee. Go ahead.
Florida's lottery game Lotto is set up so that each player chooses 6 different numbers from 1 to 53. If the 6 numbers chosen match the 6 numbers drawn randomly, the player wins or shares the top cash prize. As of this writing, the top cash prize has ranged from $7 million to $106.5 million. With 1 Lotto ticket, what is the probability of winning this prize?
Okay. And does order matter?
Yes.
For the lottery.
It does.
It does.
Does?
Okay. So all you gotta get is the 6 numbers. It doesn't matter what order they're in. And that's why sometimes they end up with more than 1 winner. So,
Share that money.
will we do a permutation or a combination?
Combination.
Combination?
Yes, but
Yes.
if two people win, do they have to share the money?
Yes.
Oh, that sucks.
That's what.
So you have numbers, and we're not talking about digits like from 0 to 9. We're talking about numbers from 1, 2, 3, 4, all the way to 53. So out of 53, you're going to choose 6, and the order does not matter. Oh, sorry. I was thinking about 6 already. And so the formula for that one, it goes like this. Well, it is n factorial over n minus r factorial. And since here we have to eliminate all the ones where the order matters, we also divide by r factorial. So if we substitute that into here, if we will have 53 factorial over.
That's a big number.
Why do I keep saying that?
That's a big number.
It is a really big number. Hold on to it. Don't spoil the surprise. 53 factorial divided by 53 minus 6 factorial times 6 factorial. And so this will be 53 factorial over, I'm sorry, that's not what I meant to do. Oh no, yeah, it was. 53 factorial over 47 factorial and 6 factorial. And you in fact can enter this whole thing on the calculator for your take-home exam, as long as you show me a formula, a substitution. You can enter this on the calculator and then get me the answer. I will be okay with that. So what is it, Peru?
I don't know. It's
Oh!
Big. Well,
It's
'cause I,
229574.
Wait, 2295?
5748.
what?
Whoa, so there are 22 million possible combinations.
Almost 23.
And the order doesn't even matter. Imagine if we consider the order. It will be a lot more. Actually, what is 6 factorial?
Let's see.
Is it 720?
Yeah.
It will be 720 times more than this, if the order was to count. Okay, so if you are hoping to win the lottery,
Good luck.
I think your chances of getting some luck in Vegas might be higher. Until you're 21. I want to make that very clear. Okay, probability of an event not occurring. Let me see, how many slides do we have left? Okay, I think we can finish this one, and then that will be the last one. Okay, so probability of an event not occurring. What was the probability when we say 100%? How do we say that as a decimal? 1, just 1, right? In this case, it's a whole number, an integer. So that's the probability that an event will occur for sure. So the probability that certain event will not occur is going to be the probability that it will occur minus the probability of the opposite of this. Okay? So let me show you how this works. Remember the example with the die, right? I'm not going to take too long drawing. Okay. So how many outcomes do we have in there? 6, right? So what is the probability of not getting a 1? So it will be 1 minus the probability of getting a 1. And so this will be 1 minus 1/6, and yeah, you guys were very quick to tell me 5/6. So that's what it means, okay? So when I say the opposite of this one, that's what I mean. The probability of not getting 1, the opposite of that will be the probability of getting a 1. So let's look at this question here. We're going to use that graph. And yes, it is a real graph from the Census Bureau. And it states the world population by continent and region. And so we have Asia, have a lot, right? Because China, India, and right here we have Africa in purple, Europe, North America, so that's only including Mexico, Canada, and the US. We have South America, and hey, where's Central America?
No, Oceania is like Australia and all those islands.
Okay, anyways, let's answer the question before the class is over. So, the graph shows the distribution by continent of the world's 7 billion or 7,000 million people. Keep in mind that this was probably in 2010.
Well, actually, now we have 7 billion.
I'm not sure.
2010 probably had 7.
If one person is randomly selected, find the probability that the person
Hold on.
does not live in Asia. Okay,
Let's go.
so the probability of not from Asia. And so that will be 1 minus the probability that the person is from Asia. And so that will be 1 minus how many?
4,230 over 7.
And tell me, Sean, why are you telling me over?
Because that's what we do.
That's the total, right? The sample space. So yes, we have to consider that. Now, I know you guys don't like fractions that much, but you can do this one pretty quickly, because this will be 1 is 7,000 over 7,000 minus 4,230 over 7,000.
Does it matter if you don't add the other extra million?
Which million?
Because it's 7,000 million, so
Because it's what?
it's 7,000 million, not just 7,000.
Oh, but this one is also in million.
Oh, yeah.
Yes, they're all in million. That's why I use 7,000. Can we get a decimal, please? Just do 1 minus.
Oh, 0.3957.
So that's the probability that if you choose one person randomly out of 7 billion, that person will not be from Asia.
That's actually,
That includes like all the people
it's
here.
like 40%.
Yeah.
It's actually kind of,
Okay, so tomorrow you guys will finish this lesson, okay? Do not ditch, please.
I'm not gonna be here tomorrow.
I adjusted my math homework, so